All right, we'll be continuing our discussion of Chapter 10, and we're going to be moving into discussing the properties of liquids. All right, so one of the most important properties of a liquid when you're working with them in a laboratory setting is density. So density is a property that is defined mathematically as the mass of the liquid over its volume. So all substances have density, but we typically deal with this in the laboratory setting with liquids. All right, so if a liquid has a high density, that means it has a high mass per unit volume, and if it has a low density, that means it has a low mass per unit volume. So when we are dealing with a mixture of liquids, let's say ones that do not mix. So I've got a beaker here with two different liquids. I'm going to have a red liquid and a blue liquid. And if they are what we call immiscible, which means they will not mix, much like oil and water, we can determine the density very quickly of the two liquids relative to one another. In this case, the red liquid is floating on top of the blue liquid. So in this case, the red liquid would be considered to be less dense, and the blue liquid would be considered to be more dense. So water kind of serves as our baseline for density. So when we look at the density of water, at 25 degrees C, it is equal to 1.0 gram per milliliter. All right, very easy number to memorize if you ask me. All right, this can also be equated to 1.0 gram per cubic centimeter. All right, or some folks would call a cubic centimeter a cc. All right, but a cubic centimeter, of course, is equivalent to a milliliter. All right, so it's 1 gram per milliliter at 25 degrees C. So you notice it is temperature dependent. And why is that? Well, if we look at the equation for density, and it's equal to mass over volume, all right, mass is not affected by temperature, all right? However, volume is, all right? We learned back in your gas laws that volume and temperature are directly proportional. So if you increase the temperature of a gas, it will occupy a greater volume. All right, so that also happens to liquids. So density is definitely temperature dependent. So be aware of that. But when you look it up, 25 degrees C, it's 1 gram per milliliter. All right. Another property of liquids that we have to study here is something called surface tension. And this is quite a neat little property that we have to invoke our discussion of intermolecular forces again. So if I were to look at a container of water, and I'm going to have the surface of the water there, all right, and I'm going to draw a little cartoon if I had a sphere of water sitting at the surface and a sphere of water, or I guess we could call it a particle of water, below the surface. All right, so I'm going to draw neighboring water particles. Now, it's not to scale. All the water particles should be the same size. And in each case, each one of the water particles are surrounded by neighboring water particles. However, you notice the one at the surface is not completely surrounded, right? That's because once you break the surface, there's no more water, all right? So we have two different scenarios here. A water particle at the surface is experiencing a different environment than a water particle below the surface. So as we know, with the intermolecular forces, especially those with water, they're quite significant. So I can imagine that the surrounding water particles are pulling my particle at the surface in a net downward direction. All right, so what's going to happen is my water particle at the surface is going to be pulled down. However, my water particle below the surface has a net effect of 0, all right? All the particles around it are pulling with the same intensity, therefore that particle would remain relatively static, all right? It does not experience a net downward pull at all. All right, so what's going to happen here is we're going to see a net pull downward on the particles at the surface. All right, and of course there's more than just one particle at the surface. So what we're going to imagine seeing is that our water, it doesn't change colors, but you get the point. Particles at the surface are being pulled downward, and we're having a something where we minimize the surface area at the top of the container, all right, where the surface of the water is, and this gives us something called surface tension, right? So that's that tension. And you can take advantage of this surface tension in water. Many of you may have tried to put a paper clip, let's say, on water, and if you're very, very careful, you can actually have the paperclip float on the water. All right, and the reason why, even though the paperclip is more dense than water, it should sink. You can take advantage of this surface tension where it will not want to break through those water particles at the top that are filling that net downward pull. But if you just jam it in there, you'll get it below the surface and it'll just sink. All right. I think there's little insects called water skeeters or water skaters. They also do the same thing with their legs. They can just barely put the weight of their legs on the water, and then they can skate across the water. All right, another property that we're going to look at. Oh, before we get into that, let's compare surface tension of two different liquids. All right, so we're going to look back at water versus pentane. All right, and again, let's just draw some molecular representations of water, and then of course we know pentane is our little 5-carbon hydrocarbon molecule. All right, and I will go ahead and pose the question, well, which one's going to have a greater surface tension? All right, and the way you can answer that is going back to this picture here, and you say, well, where does surface tension come from? Well, it essentially comes from intermolecular forces, right? You have this net downward pull of surface particles by neighboring particles. So the stronger that net downward pull, you imagine the greater the surface tension. So who's going to have a greater intermolecular force interaction with each other? And the answer for that is going to be water. All right, water has that hydrogen bond capability, whereas pentane does not. It only has the dispersion. So we can actually quantify these two numbers. Water has and you don't have to memorize these by any means, has a value of 7.3 times 10 to the minus 2 joules per meter squared. All right. So joules, of course, is energy unit. All right. And then the meter squared is for our area. And to give you an idea, pentane is considerably weaker at 1.6 times 10 to the minus 2 joule per square meter. All right, so quite a significant difference in surface tension between water and pentane. So if you were trying to float a paper clip on liquid pentane, you would probably have a very difficult time doing it. All right. Okay, next one I want to look at is viscosity. So viscosity is, verbally defined as the resistance of a liquid to flow. All right. So when I'm talking about flow, all right, that that just means it's another molecule slipping by another molecule as it would be going downhill, right? Like a flowing of a river, of course. And we've all seen this in the kitchen. You would imagine that things like honey, syrup, those would be viscous liquids, where things like water would be less viscous than something like honey. All right. So this is actually measured in a lab by dropping a standard mass through a liquid. All right. And the rate of which that standard mass falls through the liquid determines its viscosity. All right. So there are several different units for viscosity. One that's quite handy is something called poise, named after a scientist. And it has the units of capital P, which is kind of inconvenient because it sometimes gets confused with pressure. But that is gram, that's the standard mass, how many centimeters it falls per second. All right, so that is the idea. That's how they measure viscosity. It is more conveniently expressed in units of centipoise. All right, so this is just poise, 10 to the minus 2 there, kind of like a meter and a centimeter, of course. So centipoise is a handy unit to measure viscosity in. And just to give you an idea of some common liquids in the laboratory and their viscosity levels, all right, we have pentane, water, and something called glycerol or glycerin, all right? And let's go ahead and draw their structures. There is our pentane, and then water. And here's glycerol, one that we have not yet seen. Right, it's an organic compound, but it's not technically a hydrocarbon. All right, it has carbons for sure, but it also has these OH groups, which we call hydroxyl groups. All right, or alcohol groups, but hydroxyl is a little more accurate. So it has quite a bit of this hydrogen bond donation capability here, all right, for its surface area. So let's go ahead and put some numbers to these guys. So I'm going to write CP up here. That's their counterpoise. And this is at 25 degrees C. All right. So it turns out that viscosity is temperature dependent. All right. And that shouldn't be a surprise. There's that old saying, slow as molasses in January. Right. That's because molasses is intrinsically viscous. And if you cool it down, it's going to be even more viscous. All right. So as liquids are heated up, they can flow faster by each other. It's because their intermolecular forces are eased as temperature goes up. But nonetheless, let's get to this. Pentane 0.240. All right. So do we expect water to have a higher viscosity or a lower viscosity? Well, water having stronger intermolecular forces than pentane, I would imagine that water is going to have a higher one. And looky there, in that handy, it's rated at 1. All right, so that's kind of the standard number there. But then we go to glycerol. Check this out. 1.49. That's a terrible looking 9. 1.49 times 10 to the third. All right, so nearly 1,000 times more viscous than water. All right, so glycerol, you may have seen this. This used to be kind of an over-the-counter laxative. It really isn't used for that anymore. A lot of people, you can buy it at the pharmacy still, but if you look up, you can actually take water, soap, and glycerol, which you can buy at the store, and make your own bubble solution, and you can make bubbles at home. Okay. Next thing I want to go into is we're going to start talking about phase changes, and we're going to start looking specifically at the phase changes between liquids and gas, or liquids to gases. That's a very interesting area of phase changes, especially in the laboratory. But nonetheless, what we're going to get into is just phase changes. And, for most of us, this will be a review. However, we kind of need to talk about some of these definitions. All right, so as we go from a solid to a liquid, all right, that, is a phase change I'm certainly we've all seen, melting of water, for example. So that's exactly phase changes, not changer. Solid to liquid, all right. This can be known as melting, and going in the other direction would be fusion. All right, so that would be the equivalent names there, okay? So when we go from a liquid to a gas, this would be known as boiling or vaporization. And as we go from a gas to a liquid, in reverse, that is called condensation. And if we go from liquid to a solid, right, so that is commonly known as freezing. Okay, there's some other ones that we need to review that are probably not quite as obvious. Gas to a solid. All right, this is bypassing the liquid phase. So what we're doing here is we're taking a gas and converting it to a solid by never going through the liquid phase. All right, that is totally possible, as we'll see later when we look at these phase diagrams. But this process is called deposition. And we can go in the other direction. We can go from solid to gas directly by never going through the liquid phase, and this is called sublimation. All right, a common material that is, well, not a common material, but a material that you may have seen before is carbon dioxide does this. All right, so carbon dioxide, we can go from solid carbon dioxide, which is called dry ice, because it is very cold and used for shipping, temperature sensitive materials, but it doesn't, get wet, and that's because it bypasses this liquid phase. So they call it dry ice because it's cold and it goes straight to the gas phase and never hits the liquid phase at standard pressure. All right. Okay, now we kind of want to look at the thermodynamics of phase changes. All right, so we're going to talk about this in the terms of something called enthalpy. And a change in enthalpy, you've learned, has been given the symbol delta H. All right, so if delta H happens to have a positive sign, that is called endothermic. Let me see if I can cram that word in there a little bit better. What this essentially means is that it is absorbing heat. All right. And if delta H is negative, this is an exothermic process. And this means it is releasing heat. All right. So what we're going to do is we're going to take a few phase changes and we're going to see whether these are endothermic or exothermic processes. All right, so let's do something very simple first. Let's go ahead and take a solid, and we'll say we have ice, all right? And what we're going to do is we're going to phase change to the liquid phase, which we'll just call liquid water. Now, you don't have to use water in all these cases, but that's just something we have probably the most experience with. So my question is, if you want to go from ice to liquid, well, what do you want to do? All right. Well, this process, of course, is called melting. All right. So if you wanted to melt ice, most of us would agree that adding heat is what we need. All right. So we're going to do what? We're going to add heat. All right. So if we're going to add heat, is this a process that requires heat or releases heat? Right. Well, adding heat means that we require heat or absorb heat. So going back to our definitions here, is this an endothermic process or is this an exothermic process? Well, the correct answer is that it is an endothermic process. All right, cool. So let's take it a step further. Let's go from liquid water to vapor, okay, or steam. All right. Well, if you want to do this process, this is boiling. All right. We're going to have to add heat here. So this process would be endothermic. All right, and this is the whole idea behind sweat. All right, when you get hot, you sweat, so therefore liquid water appears on your forehead or wherever, and then the heat from your head is absorbed, right, because it's endothermic, and it's converted into steam, and then it cools you off. All right, so sometimes on those cold nights in Pittsburgh, you'll see the football games, and the players come onto the sidelines, take off their helmets, and their heads are steaming, right? Well, it's because they're sweating liquid water. Heat is being absorbed from their bodies, thus cooling them off and being steamed off for a pretty cool camera shot. All right, so let's kind of recap here. If we go from solid to liquid to gas, all of these processes going from left to right require heat. So going in that direction is endothermic. All right. However, if we go in the opposite direction, gas to liquid, all right, and then liquid to solid. So we're going from condensation to freezing. All right, those are exothermic processes. All right, and that's a little bit counterintuitive, right? Because if you think about freezing, well, where do you do freezing at in your house, for example? Okay, so you take liquid water and you put it in the freezer, and then it becomes a solid. That's an exothermic process, all right? So what does that mean? It means it's releasing heat. That's why the back of your freezer is hot, right? Because what's happening is it's having to remove that heat from the freezing process, right? So that's pretty wild, all right, to think about. So as you go from gas to liquid to solid, you're releasing heat, all right? So by definition, that's exothermic, and your delta H signs here would be negative. As you go from solid liquid to gas, you are absorbing heat, all right? So your delta H signs there are positive, all right? So just to kind of recap thermo and our phase changes. All right, so now we're going to get into something a little different, all right? We haven't done a lot of math or we haven't done any complicated math by any means. So what we're going to do now is we're going to start looking at some mathematical treatment of these phase changes, all right? So I've got a calculator here with me, and as I told you before, it's just a simple TI-36X. It's nothing complicated, but what you'll need to do is follow along with the calculations on your calculator and ensure that you can get to the same numbers that I'm getting to, and it's going to require some comfort with manipulating algebraic expressions, and of course comfort with your calculator. All right, so what we're going to be moving on to next is our discussion of evaporation, vapor pressure, and boiling point. Okay, so first thing, we know what evaporation is. We just talked about it. That's going from a liquid to a gas. Boiling point is the temperature where that happens, but vapor pressure is a new word for us, all right? Or one that may not be as familiar as the other two. All right, so when we talk about vapor pressure, all right, what is that? All right, this is the pressure exerted by molecules, or I guess we could say particles, that have reached the vapor phase. All right, so let's put together a little cartoon here to explain what that means. All right, so if I just had a container of water here, all right, and I've got particles at the surface, all right, and since they're at any temperature above absolute zero, they're going to spontaneously escape into the vapor phase, all right? How many of those will? Well, that depends upon temperature, all right? So the greater the temperature, the more of those particles are going to escape, all right? So at lower temperatures, I have less particles escaping, and at higher temperatures, I have more particles escaping, all right? So what I can actually do is put let's say, a seal on top of my container and then hook it up to a pressure sensor. And I'm just going to put atmospheres here. All right. So what I can do is I can start adding heat to this container. And you imagine as I heat this container, what's going to happen to the value on my pressure sensor. All right. So if I increase heat here, I'm also going to increase pressure. All right. So more of those particles are going to escape. All right. As I heat the container. But remember, I'm at a heat value of anything greater than absolute zero, so I'm always going to have some sort of vapor pressure, all right? So I'm always going to have vapor pressure that's non-zero, essentially, okay? So what we can say here is something about vapor pressure and boiling point. Okay, by definition, a liquid is boiling when the vapor pressure is equal to the atmospheric pressure. All right? So that is the definition of boiling. All right? Vapor pressure is equal to atmospheric pressure. All right? So let's go back to our little cartoon, and I'm going to draw this. I'm going to have my particles, all right, on the surface, and then some of them are escaping. All right? So let's say this is water. All right? So at 25 degrees C, water would not be boiling, all right, in our experience, all right? If, you walk up to a cup of water at room temperature, I would not expect it to just be spontaneously boiling, right? That's not going to be the observation that we expect at 25 degrees C. And the reason it does not boil at 25 degrees C is because the atmospheric pressure is stronger than the vapor pressure. All right. So what we can do is we can say P-vap, vapor pressure, versus the atmospheric pressure. Which one's bigger? At this point, the atmospheric pressure is greater. Therefore, it's keeping those molecules, or a heck of a lot of them, down in the liquid phase. All right. What happens if we start reducing the atmospheric pressure? All right, that's pretty cool idea. And that's exactly what you would do with a vacuum. All right, so if we started removing the atmospheric pressure, and let's say we removed it to zero, right, which is impossible, but if we could, what would happen if we took the atmospheric pressure away at 25 degrees C? Okay. At 25 degrees C, if we take the atmospheric pressure away, what would you expect the water to start doing? And the answer is it's going to start boiling, all right, because there's nothing pushing those guys down, all right? So water is going to start boiling at 25 degrees C. Now, have you ever seen that happen? No, because you're not living in a vacuum, all right? There is atmospheric pressure. However, if you were to put the glass of water into a vacuum, you would watch that water. As soon as the vacuum was applied, that water would start boiling, which is pretty wild. All right. Now, let's go back to the non-funky world where we actually have an atmospheric pressure. Okay. What happens is we start to increase the temperature. All right. So let's go to 75 degrees C. Now, we all know that the boiling point of water is what? 100 degrees C. Now, would water be boiling at 75 degrees C? In your experience, it should be no, all right, because we expect it to start boiling at 100 degrees C. However, the vapor pressure is increasing, all right? So I'm going to go ahead and show this in our cartoon that our vapor pressure is increasing, all right, with that little cartoon vector there. But it's still not strong enough, all right? But then, if we get to 100 degrees C, what's going to happen is that the vapor pressure is going to overwhelm the atmospheric pressure, all right, or become equal to it. Therefore, we're going to start seeing the water boil, all right? And then if you go any higher temperature, is it going to matter? And the question is, can you go to a higher temperature? All right. Well, when water hits 100 degrees C, it's releasing particles into the vapor phase. All right. Thus, you cannot heat the water any higher. All right. So the maximum temperature water can get is going to be 100 degrees C. Now, there's some tricks you can play to change that. All right. And we'll talk about that here in a moment. But everything at atmospheric pressure tells us that you cannot heat water above 100 degrees C, all right? Because what's going to happen is the water is just going to go into the vapor phase, all right? So water can't be heated any higher than 100 degrees C at atmospheric pressure, all right? And we'll come back to some tricks here in a little bit, all right? But let's just try to plot this. So I'm going to plot vapor pressure versus temperature, all right? So my y-axis, I'm going to put vapor pressure, x-axis, I'm going to put temperature, all right? So we know water, and this curve will be for water, is going to boil at 100 degrees C when we're at atmospheric pressure. So atmospheric pressure is defined as 1 atmosphere or 760 millimeters of mercury, right? Those are interchangeable units there. But what temperature is water going to boil at 1 atmosphere? It's going to be 100 degrees C, all right? So this is an intersection that we're expecting to see, all right? We're going to cross the 1 atmosphere mark at 100 degrees C. So what that means is when the vapor pressure equals the atmospheric pressure, that's the boiling point. And we know the boiling point of water is 100 degrees C. But what's interesting is the rest of this curve, all right? It just looks like that, and it's not linear, okay? It's curved. So why is this not linear? And what I mean by linear is it's a straight line. That's not what we're seeing here. What we're actually seeing is something more like this, all right? An exponential like curve, all right? So why is it exponential? Okay, well, what's happening as you increase the heat, all right? You're having, what, more and more particles escaping, all right? And as you increase the heat, more and more particles escaping is going to do what? Exert more and more of a vapor pressure, all right? So we're not seeing it in a linear fashion, we're seeing it in an exponential fashion, all right? And this was defined by a very famous equation called the Clausius-Clayperon equation. So what they were able to show is that if we plot the natural log ln of the vapor pressure versus 1 over T, we can get a linear relationship between vapor pressure and temperature. All right. So a lot of times when you have an exponential function and you want to straighten it out, taking a natural log or a logarithmic a transformation of it will help. And the 1 over t, that's just going to give us a negative slope here. All right. So what we're going to see here is the ln of p versus 1 over t, and our plot will look like this. All right. So it's now linear, right? And notice it has a negative slope. All right, it's because we're going with a 1 over t here. All right. So this equation, since it's a linear line, we have ln of p vap equals negative delta H of vaporization over R 1 over T plus some constant C. All right. So this has a very familiar form of what? Y equals M X plus B. All right. Our old friend Y equals MX plus B. All right. So this was a very clever way to take a complicated exponential relationship and make it into a nice, pretty linear relationship, as we can see here. All right. So what does this equation allow us to do? Well, the Clausius-Clayperon equation can tell us we can calculate delta H of vaporization, which is very handy to know for a substance, if we measure the vapor pressure which can be done experimentally at a specific temperature. All right. And once you know delta H of vaporization, you can go through and build the entire curve, all right, by using the Clausius-Clayperon equation, all right? So once the delta H of vaporization is known, then we can go through. So just to recap what that equation looks like again, all right? ln of p vap equals delta H vap over R times 1 over T plus C. So we can measure the PVAP, all right? We can measure the temperature, and then R is the gas constant, and then we can calculate delta H of vaporization. Once we have delta H of vaporization, at any temperature, we can calculate what that vaporization pressure is going to be, all right? So this is a very, very useful equation, all right? And before we start using it, I just want to kind of go back and review some properties of logs, specifically the natural log, all right? So just a little mathematical back check here. So if we have the natural log of some function a, and it's equal to x, in order to figure out or solve for a in this case, all right, so we have some value. If we want to solve for a is going to be equal to the exponential of x, right, or e to the x. This also works for logarithms, all right, so if we have log 10 of a is equal to x, if we want to solve for a in this case, a is equal to 10 to the x, all right. So natural log is based on the exponential function, whereas logarithms are based off powers of 10. All right, so just keep that handy and just remember that relationship. Also, a neat little trick with logs and natural logs too is that the ln of a over b is equal to the ln of a minus the ln of b. All right. Likewise, the ln of a times b is equal to the ln of a plus the ln of B. All right, so keep this slide handy when you're cranking through some of these problems in the homework. All right. So what I'm going to do now is go ahead and work through an example. All right, and of using this equation. So, before we do that, it's important to define that the Clausius-Clayperon can be written in what we call the two-point form. I'm just going to call it CC for short, the Clausius-Clayperon equation. So I'm not going to go through this derivation, but what we can do is we can set two Clausius-Clayperon equations up for two different temperatures, all right, and two different vapor pressures, all right. And since they're going to have identical gas constant and identical heat of vaporizations, we can do a few mathematical manipulations, and what that's going to give us is that the natural log of pressure 1 over pressure 2, all right? So when I'm talking about pressure 1 and pressure 1 is the vapor pressure at one particular temperature, and P2 is the vapor pressure at a second temperature, all right? So it's the same substance, it's just two different temperatures. So since it's the same substance, it's going to have the same heat of vaporization, and it's also going to have the same gas constant, all right? And we're going to have the two different temperatures here, all right? So T2 and P2 are related, and T1 and P1 are related, all right? So this equation is very handy when you're trying to calculate, let's say, a heat of vaporization from two different experiments, or if you want to calculate what is the vapor pressure going to be of this substance at a new temperature, all right? So this equation, the two-point form, is quite helpful, all right? So let's actually put this, this equation to use, and we're going to say, all right, the vapor pressure of ethanol at 34.7 degrees C is 100.0 millimeters of mercury, and the delta H of vaporization is equal to 38.6 kilojoule per mole. What is the vapor pressure of ethanol at 65.0 degrees C? All right. So this is where we're going to have to use that two-point form, all right? What do we have? Well, we have, it looks like, a temperature here. We'll go ahead and call this T1 because it's the first temperature we ran across. We could have called it T2, T78, it doesn't really matter. But we're just going to call it T1 because it's the first one that we ran across. And it's also telling us that we have a pressure here at that corresponding temperature. So since it's corresponding to T1, I'm going to call that P1. I've got the delta H of vaporization, and it's asking me for what is the vapor pressure at that temperature. So this is what I need to figure out. This is P2, which I have no idea what that value is at this point. That's what I'm going to have to calculate. And here is my T2. All right. So that's the information I have. And what I'm going to have to do is, on the next slide, is put that information on the slide, write the equation, see what I have, and see if there's any manipulations to the numbers I need to do, because units are always key, right? We got to figure out what units we're working in and all that good stuff. So let's go ahead and get to work here. All right. So back to the equation, the two-point form of the Clausius-Clayperon. It's the ln of P1 over P2 is equal to the delta H of vaporization over R, 1 over T2 minus 1 over T1. All right. Now, typically, constants are going to guide what units you use. All right. So the gas constant right here, R, all right, since we're dealing with kilojoules and joules and all that good stuff, our value of R that we're going to use is the 8.314 joule per mole K. All right. So my units of energy need to be in joules. Looks like I'm going to be dealing with perhaps per mole here. And my units of temperature need to be in absolute temperature or Kelvin. All right. Is there any guidance on what units of pressure I should use? All right. Not from this constant. All right. So let's see, what was my delta H of vaporization? That's another constant that I was given. All right. It's at 38.6 kilojoule per mole. Okie doke. No guidance on pressure there, but you'll notice that we're dealing with two different units of energy. We're dealing with a joule and a kilojoule. All right. So I'm going to have to convert that somehow. All right. To make them both kilojoule. So I typically find that just dividing converting the kilojoules to joules is a little easier for me. All right. So in order to do that, just to kind of demonstrate how I would do it, 38.6 kilojoule per mole. All right. And I'm going to say that there is 1 kilojoule in 1,000 joule. All right. So my kJs will cancel. And all I have to do is just multiply my 38.6 times 1,000. So the easiest way to do that is 38.6 times 10 to the third joule per mole. All right. So that's the delta H of vaporization that I'm going to use. Likewise, you could have divided your 8.314 by 1,000. All right. And you could have 8.314 times 10 to the minus third kilojoule per mole K. Either way, you just need to clean that up and figure out your favorite way to do it. All right. Still no guidance on pressure. But what's cool about it is, look, in the equation, it's P1 over P2. So the units are going to cancel. So your units could be in bar, torr, atmosphere, PSI, doesn't matter because the units are going to cancel. All right, so whatever we were given, let's see, looking back, we were given millimeters of mercury. Those are going to cancel, so we're cool. All right. So let's try again. I don't have as much room on this screen as I do a full piece of paper, but I'm just going to kind of restart where we were at. Okay. So what was provided to us? We said P1 was 100 millimeters of mercury. P2, that's unknown. That's what we're searching for. Okay. Delta H of vaporization, that was 38.6. We converted that one, right? Let me just check. Yep. Times 10 to the third joule per mole. Our gas constant, 8.314 kilojoule per mole K. T2, all right, we were given T2 as 34.7 degrees, or sorry, T2 was given at 65 degrees C, all right? So we need to get that to absolute temperature. So 65 plus 273 gives me 338 K. And T1 was given at 34.7 degrees C, which we're going to add 273 to that, and we get 307 K. All right. So we've got everything we need except P2. All right. So that looks like kind of a monster equation to get P2 out of. All right. So how are we going to deal with that? All right. So I'm going to show you my stepwise way of trying to simplify this equation. I like to work in it in chunks. All right. So the first chunk I like to take care of is the temperature chunk. All right. So what I'm going to do is plug in my two temperatures and simplify that part. All right. So the part that I'm zooming in on is this 1 over T2 minus 1 over T1. All right. So what I'm going to do is 1 over my T2, in this case, is 338 Kelvin. And my T1 is 307.7 Kelvin. All right. So I need to work on that. And this can be kind of clunky in your calculator. All right. But I recommend just taking your parentheses, open parentheses, 1 over 338 minus, open parentheses, 1 over 307.7. All right. And when you do that, I get a value that is negative. Why is that? Which is totally fine. I forgot about the negative slope here. So when I get that negative number, I'm getting negative 0.000291 1 over Kelvin here. All right. I can simplify this number to negative 2.91 times 10 to the minus 4. And I'm going to go ahead and dump my units because I know that I'm okay with Kelvin right now. Okay, so it's just going to make life a lot easier if I don't carry that 1 over K around. All right, so going back to where we were, we just finished that chunk there. All right, so I'm going to do another chunk in yellow. That's going to be the delta H of vaporization over R. All right. So this one will be quite straightforward because we're dealing with a constant. All right, so that is the 2 constants, 38.6 times 10 to the third joule per mole divided by 8.314 joule per mole K. All right. So you'll see now that my joule per moles will cancel. And I just simply punch this quotient into the calculator. So this, again, is something you want to follow along with and make sure you can do. And I get 4,642.8 1 over K. All right. So let's go back to our master equation. We've got the yellow chunk and the red chunk, and all we have to do to those two chunks is multiply them. All right. So what I'm going to do is take those two numbers and multiply them together. So the two numbers I got were, be nice if I could remember them, the 4,642.8 times the negative 2.91 times 10 to the minus fourth. All right. So when I do that, I'm getting pardon me. 1.35, negative 1.351. All right, so where are we? We now have taken care of the entire right side of the equation, and we've gotten a number. All right, so again, carrying that 1 over k number is kind of annoying, or unit, so it's easier just to take this number here. All right, it's negative 1.351. All right, that's the right side of the equation. So we're going to set the left side of the equation, which was the ln of P1 over P2, equal to negative 1.35, and how many sig figs did I go? 3, 1. All right. Again, what are we searching for? Searching for P2. All right. So we need to isolate P2. And how we're going to do that with these logarithms. All right. So that's why we have to go back to those, the slide I showed you where we were talking about how to operate with logarithms. So we can simplify this equation. You could arguably simplify it by breaking the quotient up into a difference. All right, so the ln of P1 over P2, of course, is equal to the ln of P1 minus the ln of P2. And that's still equal to negative 1.351. And we know the value of P1, all right? So we can actually plug that in. And P1 was 100 millimeters of mercury. We're just going to leave the units off because they don't really matter at this point. Oops. So what I'm going to do now is take the natural log of 100. So on my calculator, I'm going to do ln 100, and I get 4.65. Sorry, 4.605 minus ln of P2 equals negative 1.351. So I'm going to subtract 4.605 from both sides. So I'm going to do that on the next slide. So next ln of P2. Remember that negative sign stays out there. So this is negative 1.351 minus 4.605. All right. So this is just simple arithmetic here. A negative 1.351 minus 4.605. That gives me a negative 5.956. So minus ln of P2 is equal to that. So since I have a negative sign in front of each one, I can essentially multiply the whole equation by negative 1. That gives me ln of P2 equals 5.956. All right. And what I'll have to do now to isolate P2, remember, ln of A equals x. If I want to solve for a, I need to do e to the x. All right. So what I'm going to do here is P2 is equal to e to the 5.956. All right. So on your calculator, you want to find the exponential one, or the e, 5.956, and I get P2 equal to 386. 386 what? All right. You have to go back to what pressure you were doing P1 with, and that is millimeters of mercury. So there, lo and behold, is our vapor pressure at 65 degrees C. All right. So that is a very arduous process to use the Clausius-Claperon equation, but make sure you practice this one and you go through the same, arrive at the same numbers I do when I'm working in those chunks, all right? And there'll be a couple homework problems to practice the Clausius-Claperon equation, all right? That is going to be the end of this video. Thank you very much.